Okay, so let's get started. Welcome, everyone. My name is Sri Krishnamurthy from Quant University, and this is guest lecture 4 of the Quant University Artificial Intelligence School. Every fall season, we host a artificial intelligence school focused on the various topics which are in the frontier in the artificial intelligence realm. And obviously, with the progress of artificial intelligence, which has been happening over the last few years, we have seen tectonic changes in the topics and the interest and the methodologies which have been happening. So to keep up with all the things which are happening, both on the academic side of things, on the industrial developments, and also on the regulatory front, we bring in experts in the field who are working on these methodologies, either in the context of regulation or in the context of innovation, or also in the context of applying these in various settings. And with the focus of financial services, we have a lot of people in the financial industry who attend these events. And I'm pleased to invite today Dr. Apostol Vassilev from the NIST, who has been working on various cybersecurity issues for a long time and now has been focusing on artificial intelligence, security, and risk management. I have the pleasure of knowing Apostol for many years now, and he also collaborates with Alina Opria, who is a professor at Northeastern University, and he's going to present some of the work today, which is based on a report which NIST released early this year, focused on adversarial machine learning. But before I get started and invite Apostol, so I'm going to share a few slides just to introduce people to what we have been up to over the last few weeks. So give me 1 second. Let me quickly share my slides. So today I'm going to be primarily introducing the various sessions we have been having, and I will hand off the stage to Apostol, who is going to be presenting the talk on the adversarial machine learning. As most of you know, Quant University has been hosting these sessions over the past many years, and this year we have been working on a couple of different courses. We had a whole session on artificial intelligence in investing in October as a part of the Boston FinTech Week in Boston. It was very well attended, and the recording is available on the Quant University libraries at qu.academy. And in November, we are going to have a full day course on generative AI, ChatGPT, and applications for financial professionals. And in December, we are going to have a session on use cases and case studies. These sessions are predominantly attended by people in the industry who are interested in spending a whole day working on various use cases. So if you're interested in this full day sessions, please send an email to info@qsandbox.com, and also some of the details of these sessions will be available on the Quant University website. In addition, we have the Quant University AI Fall School, which are the Zoom sessions we are hosting every week. And this is lecture 4, what we are going to have today. Next week, we are going to have Julia Lee and Christophe Rogo from TD Bank, and Julia was heading model risk at State Street before. So we're going to have a discussion on the bank's approaches to adopting AI-related products and tying it up to the various best practices in model risk management. So we're going to have a great discussion on the experiences of what banks have been focused on and what does it take to adopt AI and model risk management and integrate these best practices. So stay tuned for that. I know it's election day and people will be tuned towards the results, but hopefully you'll make time between 12 and 1 next week to kind of get an additional perspective on how various practices are being used in the industry. And we also have a couple of new sessions coming up in November. Uday Kamath, who recently wrote a book on large language models, and he's going to be having a full session on artificial intelligence metrics. So he's at SMARsh. And then also Rafiq, who's from Fifth Third Bank, he's been building a framework on leveraging generative AI and various aspects within the smaller bank setting. So he's going to be having a session focused on his framework and various topics associated with that. So we're going to be continuing to add new sessions. And if you have any recommendations for speakers or topics you would be interested in hearing, please do send us a note and we will bring those speakers over the next few weeks. And with that, I would like to hand over the stage to Dr. Apostol Vassilev. So he is pioneered various approaches in the context of adversarial machine learning. And I really loved the rigor and the depth to which the paper, which is going to be referenced in the chat window in a few minutes. But I really appreciated his taking time to spend with us talking about the various aspects on the taxonomy and the attacks mitigation associated with adversarial machine learning topics. Now, as you all know, artificial intelligence has gone through a lot of innovation over the past few years. The artificial intelligence risk management with initiatives by the NIST, with ISO, with the EU AI Act, has come to the forefront of discussions. And people are talking about how to leverage various best practices in testing, in red teaming, but also focusing on what could potentially go wrong and how to structure the discussion so that depending on your use cases and context, you can incorporate the required best practices within your organization. So with that, I would like to hand over the stage to Apostol. So Apostol, please take it away.
Thank you, Sri. It's a real pleasure to share this stage with you and the audience and for this session on adversarial AI. Let me first share my slides. Can you see it now?
Yes, we can see it, Apostol. Yeah.
Okay, great. All right, so let's start and we'll drive through it and questions if they arise. If they're conceptual or topics that you'd like to discuss, I would defer them to the end, but something that you want to raise as in the context of a specific slide, I'm happy to take them as they go. I will not necessarily monitor the queue of questions, so if there's any, I would appreciate.
I will be monitoring that, Apostle. So if there are any specific questions, I will bring it up, and
Okay.
I'll be. And people, if you have any questions, please use the Q&A section to ask those questions, and at the end we will discuss those. But if it's really contextual, I'll bring it up and ask.
Okay.
Yeah, thank you.
All right, so we'll be talking about AI risk and threat, the AI risk and threat taxonomy. It's a document that we posted early this year. I'm going to start with one assertion, and that is that AI is useful and fun, but risky. So today, I'm not going to dwell much on the usefulness and the transformational power this technology has. We all have read about it in the media or scientific journals too much already. My take today will be on the risk side of the equation. So there's two kinds of risks associated with AI systems. The first category is the so-called inherent risks, and these examples of these are the unwanted bias, the hallucinations these systems have. This could be errors in the generated data, implementation flaws in the model, cybersecurity flaws in the platform in which the model is deployed. And these sort of issues are dealt with in other standards. For example, a couple of years ago, we issued a standard about managing bias in artificial intelligence. And earlier this year, as part of the executive order, President Biden's executive order on responsible use of AI, we developed a secure software development practices for generative AI and dual-use foundation model, which is a community profile, secure software development framework community profile dedicated specifically for AI models, large language models. Why is this necessary? Well, the thing is, AI models or large language models are not used as is by themselves. They usually integrated into the environment, the infrastructure of a specific business or organization, to connect it to the specific data sources that you're going to use to make the system more fine-tuned for your business needs, and therefore you'll have to connect them to databases or documents or whatever other resources you may have to introduce it in specific use cases to automate specific workflows and so forth. And so how to do that responsibly and securely is the subject of this second document. And I encourage you to take a look at this if you are considering deploying AI technology within your organization. And so the second category of risks associated with AI systems are the so-called adversarial risks. And these are the result of deliberate actions by motivated and experienced adversaries that are aiming to disrupt, evade, compromise, or abuse the operation of the model or its output. And this is the kind of, these are the risks that I'll be talking about for the rest of my presentation. Okay, so to characterize the landscape of adversarial machine learning, we issued a new NIST standard, NIST AI 100-2 edition 2023 in January of this year. This was a collaborative effort with Professor Alina Oprea. She already mentioned her. She's with Northeastern University and a well-known expert in adversarial machine learning. She's also a faculty appointee at NIST at my team, and I'm very happy to collaborate with her on this and other initiatives. We were fortunate to have two experts from the industry, Ali Fordes and Hiram Anderson from Robust Intelligence. They are now, Robust Intelligence recently was acquired by Cisco, so now they are with Cisco, but they are both also leading experts in the adversarial AI space. So as you can see, this report is really a collaboration between government, academia, industry, and as such, it's really typical of how NIST approaches development of consensus-based standards in an open and transparent manner. We intend to maintain this standard annually, and we have just completing the 2024 edition of the standard, much updated, with significant improvements of the content and the way the content is presented. We're introducing an index to make the standard much easier to be consumed by practitioners, such that you can refer to specific attacks or mitigations by index number. Instead of just referencing specific text in a very large document. And to produce this, to develop this new version, we are joined by representatives of the two newly formed AI Safety Institute, the US AI Safety Institute, a representative from them, Maya Hamin, is joining us for the next edition, the 2024 edition of the document. And from the UK AI Safety Institute, Xander Davis is going to be joining us for the 2024 version of the document. So when we publish the document, the 2024 version, it will be open for public comments. And what we're looking for people to comment on are the latest attacks that are available for the current level of AI models as we know it, specific mitigations of those attacks. Also, we would like to get input on interesting trends in AI technology that promise to transform the industry society. Nowadays, everybody is talking about agentic AI or agents and AI agents. And this is one example of such a trend that has really developed over the last year or so. And of course, the related potential vulnerabilities and mitigations that may be applicable there. And as we go along, any terminology that emerges and needs standardization would also be helpful for us to hear from you. So one thing that I wanted to comment is that the adversarial AI space has been a really fast-moving, very large, difficult to comprehend space for the last, I think, more than a decade now. And so to illustrate this by an example, I would I would look into this graph that tries to show the plots the number of papers over the course of the last decades in the field of adversarial AI on archive.org. As you know, archive.org is the place where scientific preprints are being published. And so it's an indication of the pace of the increasing pace of development of this field over the last 10 years or so. And as you can estimate, we have about 3,500 pages total for the last decade. Fast forward to today, and just for the last 2.5 years or so, we have additional 11,354 references on archive in this field, meaning that for the last 2.5 years, we'll get 3 times more than 3 times the number of papers that have been published in the last decade. So why is this happening? Why are there so many publications of exploits and mitigations? What is going on? What's driving this growth? Well, I would suggest the following. The main reason for that, it's not just because it's a new field and there's a lot in it for us to learn and get used to and stuff like this, but the underlying problem, I think one of the most significant underlying problems is that there are no information theoretic security guarantees for AI algorithms. For those of you who are familiar with cryptography, information theoretic security guarantees in cryptography mean that in theory, if you have an algorithm that is information theoretic secure, that means that an attacker in theory cannot do anything to break it. And the only vulnerabilities occur in the practical implementations of this algorithm, either in software, hardware, or hybrid somehow. Here in AI, the situation is very different. Not only do we not have information theoretic security guarantees, but it's worse. We have information theoretic impossibility results for security, which means that the security problem is practically intractable for the existing AI paradigm. What I mean by that is that if you have an AI system or an algorithm and users will submit prompts that are completely within the valid space of acceptable parameters, you can still experience security breaches with your algorithm, unlike what I mentioned in cryptography. And that, I think, is the most significant factor that drives the enormous growth in published exploits and mitigations on archive, just as an illustration. And so our goal in devising or developing this taxonomy is not to mention every single paper that is published on archive. There are too many, and it will not be the best service we can provide to the community of stakeholders. Instead, we're trying to pick and choose those that we find the more significant or impactful in the field in order to alert people to the most dangerous attacks or the more promising mitigation approaches. So that's really how you should look at the taxonomy document, not as encyclopedia of everything, but what are the most significant trends in this domain. Okay. So as you may have seen, maybe I should mention it, that our document is part of the Trustworthy AI series of documents that NIST is working on and developed. And so the question then is, what is trustworthy AI? And we at NIST define it in terms of 7 attributes of trustworthiness. It has to be valid and reliable. It has to give you reasonable, good, valid information when you prompt it. It has to be safe. You don't want the system to give you toxic or dangerous information. It has to be secure and resilient, meaning that it should be able to withstand attacks from adversaries. It has to be privacy enhanced to be able to defend or protect the data that's inside of the model. It has to be explainable and interpretable. In other words, you should know why it reached a specific decision. It has to have its harmful biases fully mitigated, and it has to be accountable and transparent. So one way to think of this definition for trustworthiness in terms of 7 attributes is like the well-known duck test. If it looks like a duck, if it swims like a duck, if it quacks like a duck, it must be a duck. So here in our case, if your AI system has these 7 attributes, then it must be a trustworthy AI. So one comment about these attributes, people, when they're faced with this kind of definition by attributes and qualities, if you like, of the system, we all want to have the maximum score on each and every attribute, right? It's natural, it's our natural tendency to want to have, let's say, if they're rated from 1 to 10, to have 10 on everything. The problem with, and as I said, we're going to be focusing mostly on the secure and the security and resilience of the system. But to go back to the attributes, these attributes are not independent. They are mutually dependent. And what happens is that most of them are in a relationship of a trade-off. If you improve on one, you're going to have to give up on the other. For example, there's a trade-off between accuracy and adversarial robustness. There's a trade-off between fairness and robustness, explainability and adversarial robustness, and privacy and fairness. So these are well-known kind of trade-offs that have been established in the academic literature. And so what they tell us is that it's not possible to simultaneously maximize the performance of the AI system with respect to these attributes. Instead, organizations need to accept trade-offs and decide the priorities depending on the specific AI system they have, the use case in which they're working, the concrete economic, environmental, social, cultural, and so on factors in the environment where the organization operates, and so on. One systematic and promising way of looking into this problem of how to optimize the trade-offs between the various attributes of the system is through the Pareto optimality concept. And this is a case where there is no mathematically best trade-off. And so the idea here is to, when you're dealing with two conflicting parameters, the idea is to improve on one without hurting the other. And so that's essentially the idea of this Pareto optimality, and more academics and other people are looking into that approach to manage the trade-offs in AI system and the attributes of those systems. Just as an example, there is a discussion about that in the new report that is going to be coming out very soon. So I'll encourage you to look for it and check it out when you have time. Okay, so how do you go about defining an adversarial machine learning taxonomy? Well, we've looked at 4 dimensions to develop it, and these are the learning method and the stage of the learning process. Another dimension is the attacker goals and objectives. attacker capabilities, yet another dimension, and finally, attacker knowledge. And so you can see an illustration of that to the right. But one thing I want to mention right here so that you can remember it is that machine learning models can be attacked at all stages of their life cycles, from the design to training to deployment and use, something to keep in mind. Okay, so so let's look at briefly at methods and stages of learning as one of the dimensions. There's two important stages in learning that are particularly important for adversarial machine learning, and that's the training and deployment phases. The type of system, as I mentioned, is also important for deciding what kind of vulnerabilities a system may have and what kind of mitigations you may deploy at them. There's two major types of AI systems we consider in the report: generative AI systems and predictive AI systems. Generative, those examples are the present day large language models, various kinds of text to image or text to video models that have appeared in the marketplace, and so on. And predictive AI systems are, you know, any kind of recommender system that you may have for, let's say, movie recommendations or product or a sentiment analysis or restaurant recommendations. And of course, there are convolutional neural networks that are used in computer vision models. And I'll give a few examples related to those predictive models that are used in autonomous driving later in my presentation. And of course, there's different kinds of learning methods that are utilized in the machine learning technologies. You have unsupervised learning, where the data is not labeled and is put into the model raw as it is, and the model then tries to figure out what is what and learn from it. The other extreme is supervised learning, where every input data is labeled properly with a specific type, and the model is trained on this supervised on this labeled data in a supervised mode in order to learn what it needs to learn. Obviously, there's a big difference between the two. It's much labor intensive to label properly your data. So by definition, supervised learning deals with much more data sets than the unsupervised learning method. And of course, there's the sort of the trade-off between them, semi-supervised learning, where you have a small set of labeled data and much larger set of unlabeled data, and you utilize both approaches of learning. There's other types of learning, reinforcement learning, and I'll mention it a little later. Federated learning, where the idea is to not allow every model in the set of models in the federation to know everything about the data, but delegate specific parts of the learning to different models, with the idea that that if one of them is compromised, the attacker will not get the full content of the entire federation. It's basically a security related inspired architecture of learning. And ensemble learning is where you combine the results or the predictions of several different models, potentially different models, with some kind of a voting schema, whether you take the average or the maximum or some other mechanism of combining these predictions, is an example of ensemble learning. And so all of them have been used in machine learning arena. Okay, so what about attacker knowledge? Well, here we have the traditional three kinds of knowledge types: black box, white box, and gray box. This is kind of the traditional mechanism in cybersecurity, and it carries over to this domain here. In the black box case, the attacker knows nothing about the model, neither the architecture nor the training data set that was used to develop it, absolutely nothing. And the white box case is just the exact opposite of it, where the attacker knows everything about the model, the architecture, the data sets that they use to train it. So they have full knowledge of everything. And so gray box is where we have some elements, but not the full picture. Nowadays, I think with the prevalence of the transformer logic and the algorithms associated, the learning algorithms based on it, I think it's safe to say that most large language models share the same architecture, more or less. There's some variations like expert architectures and so on, but by and large they use the transformer logic, and so we can say that at least we know some bits and pieces of how these chatbots or agents are developed. We don't know the full picture. We don't know every specific one of them, which data sets were used to control it, or we may not know the exact specifics of the mixture of expert architectures that is deployed to make this particular AI service available. The black box case, where we know nothing, is more applicable to predictive models, where you have still a variety of different architectures, not all of them common for the entire class of applications that are available to predictive models. So it is possible to think of defining a proprietary architecture using proprietary data sets. So indeed, attacker will not know much about neither the model nor the data set. But the predominant generative AI technologies, I think we can safely put into the gray box category. And of course, the more the attacker knows, the more effective their attacks can be. So here is a graph or figures from two figures from the report itself. We have identified three attacker goals and objectives that they want to pursue with respect to predictive AI system on the left and generative AI systems on the right. There's three classes of objectives that an attacker may have. Availability. Breakdown is where the attacker tries to compromise the AI system so it becomes unavailable, unresponsive to the requests of the users of the service. And integrity violation is where the attacker is trying to change the behavior of the model and make predictions to attackers' choosing and not how the model was designed to do in the first place. And so finally, you have privacy objective, where privacy compromise, where the attacker is trying to exfiltrate privacy data contained in the model, which could be data in the training set of the model, or could be the parameters, the attributes of the model itself, such as the model weights and stuff like this, which in many cases are proprietary, and so exfiltrating them constitutes a privacy violation. The gray areas around each circle represents the capabilities the attacker must have in order to reach a specific objective, and the leaf nodes denote specific attack techniques. And so on the right side, we have the same three categories: availability, integrity, and privacy. And a new one, in the first version, we called it abuse, where the attacker is trying to repurpose the actions or the information generated by the model for uses that are not aligned with those of the designer or the owner of the service, in order to harm users downstream or users of the service directly. So these are the main classes of attacks, of attack objectives, and it's a good way to kind of comprehend what's happening in adversarial machine learning. Okay, so let's consider some examples. Let's take a physical evasion attack for a predictive AI system, and that's an attack against a Tesla, the computer vision capabilities of a Tesla vehicle that was published in 2021. What the attackers did is they introduced physical perturbations in the environment and where the car operates, the road. And so they try to introduce perturbations that are negligible to the human eye, but effective enough to divert the operation of the vehicle and cause it to go into the oncoming traffic lane with potential high risk for damage to the vehicle, the occupants inside, and the other road participants. Now, to devise this attack, what the researchers did was to infiltrate into the architecture of the computer vision model on the vehicle itself, and be able to introduce synthetic dots representing the physical image, the physical perturbation they wanted to plan, in order to optimize the location and the size of these to make them invisible to or negligible to the human eye, and yet effective for the vehicle. And obviously you have to run many iterations in order to find the optimal configuration. And to do that, it's best to do that in simulation or in synthetic setting. And that's what they did until they optimized the location there, and then they back extrapolated from the 2D image to the 3D surface of the road, and found the location and exercised the scenario, and found that the vehicle indeed moves in the wrong traffic lane, causing potential harm to the traffic participants. So that's a very useful illustration for how people go about devising attacks on such models. You simulate something, and only then you implement something in the real world. And one of my projects here at NIST is to develop robust AI criteria for robust AI for autonomous driving system. And we have used a similar approach to simulate attacks on computer vision models that are used in autonomous driving, and only then we implement specific in real world settings in order to confirm and calibrate our findings. But those attacks, but this work is still not published, and so I'm not going to give you specific examples. Look for that in forthcoming papers coming out of NIST on this topic as well. Okay. So just to give you an idea that this was not an isolated case or a specific situation that's only specific to a particular situation that's only specific to Tesla. The problem is much wider with say predictive AI systems that are used in autonomous driving. We all know about the robotaxis debacle in San Francisco last year, where the technology was introduced and scaled back, and one of the company was ultimately asked to withdraw from operating the service. And of course, another example is there's all kinds of reports, and here is just of crashes with the autopilot. And here is one example out of February of last year, where a Tesla vehicle crashed into emergency vehicle there. So things are, they're not anecdotal. The risks with AI are real and happening. So what can you do to actually mitigate some of these risks? So this is an example of a well-known and very effective technique called adversarial training. What it is that basically you take an adversarial example that compromises the work of the functioning of your system. You label it and you incorporate it into the training of the model. And then as the model trains, it learns how to act on such adversarial examples, and they are no longer a threat. And this technique was first introduced by Goodfellow in 2015, and then was greatly improved by Alexander Madry in 2018. And it's a good, useful technique, and it's highly recommended for improving the robustness of predictive AI systems. But if you think about it in the automotive setting, this technique, adversarial training, is reactive by constructions, because you cannot predict or anticipate all kinds of road and traffic conditions that could lead to incidents. And those are not uh, available to or hard to anticipate. And therefore, what happens in practice is that actual accident data is fed into the training of the next AI model. So sadly, we have to go one accident at a time in order to improve the robustness of the AI models that are used in this particular context of autonomous driving. One thing I want to raise here is that we are really dealing with a very difficult challenge between what I call cognitive intelligence, which is something that you and I as humans have and are able to assess unknown to us situation and devise a plausible, safe trajectory of how we should move about there, based on prior experiences and intuition. And the difference with that is cognitive task automation is what these autonomous systems try to do, and their capabilities are much, much restricted, and therefore there's a big gap between the two, and that's where a lot of the trouble occurs, where uh, autonomous systems encounter circumstances that they're not quite familiar with or haven't seen in their training, and they don't know how to deal with because they don't have what I call cognitive intelligence. Okay, so let's look at another powerful technique for improving the robustness, certifiable robustness. What is it? Well, a classifier, let's say, is said to be, or predictive system is said to be certifiably robust if for any input X, one can guarantee that the classifier's prediction is constant within some set around X. You can think of it as some kind of a abstract ball around this X in the space of input vectors. And so in that context, if you have a perturbation of input of size delta, as long as delta is smaller than a specific number r, let's say data is less than the radius r, then you guarantee that the classification of the classification of the classifier doesn't change. It still predicts the same thing as if you gave it the pure X input. But what attackers try to exploit is to insert adversarial perturbation epsilon that is small, that to a human X plus epsilon still looks like X, and yet forces the classifier to predict an incorrect class, as it is shown in this example, a classic example where you take an image of a bear and you add some noise to it, and you get a monkey all of a sudden with very, very high confidence. And so that's happening because epsilon, the relationship between epsilon and r is not absolute. What is invisible for the human eye may still be too big for AI. So you can ask the question, well, why can't I take R to be very, very large, such that if epsilon is greater, it makes it it has to be greater than R, then it will be visible to the human eye and detectable, and then everything will be okay. You could do that, but what is going to happen in that case is that because your R is so great, it will cross over the decision boundary between two different classes. And so instead of distinguishing two different objects, they all will become the same thing, let's say a panda in that case. So that means that the accuracy of your system is going to suffer. And that goes back to the initial conversation or discussion we had about the attributes of trustworthiness of these AI systems, the trade-off between accuracy and robustness. So the more you make the system robust by increasing this R parameter, making it wider and wider, you have to give up on accuracy. And on the other hand, if you want to make your system very accurate, you have to shrink the R, meaning that it becomes more susceptible to perturbation. This is just one illustration of this trade-off that I mentioned before. Hopefully, the example makes it clear now to understand. Okay, so now let's turn over our attention to the chatbots, so generative AI systems. And to do that, I'd like to go briefly over the training pipeline of the systems that should keep us kind of informed about what's going on and what kind of parameters and data sets go into it, so that we understand what are the security implications of these systems. So they start with a pre-training phase, where you have large amounts of low quality and high quantity data. This is basically the raw internet data that's fed into these models. This is the most expensive and resource intensive part of developing a model. The result of it is the base model. You've heard the reports probably by now and know that this stage of the model training can cost you hundreds, if not millions, of dollars, hundreds of thousands, if not millions of dollars, and requires a huge amount of very powerful GPU computing resources and so on. So you got the base model. The base model is good, but usually pretty rough in terms of experiences with it. So you need to kind of fine tune it. And one technique of doing that is through supervised fine tuning, where you have additional sets of labeled high quality but relatively low quality data, low quantity data, and that you use in order to train and improve the behavior of the model. And so in that case, you compute, and finally the result is a supervised and fine-tuned model, referred to briefly as SFT model. Next step is to improve further the way it acts with user prompts and develop a so-called reward model based on comparisons between of human written prompts and specific answers, all graded on acceptable and unacceptable and so forth rating. And this is also some low quantity but high quality data. And it relies on binary classification. And here the result is a reward model that you can then use as a stepping stone towards develop the next phase, which is the reinforcement learning. The rewards model is never released. It's just an internal component that an internal tool that you use in order to develop the final model, which is the RFHL model, reinforcement learning from human feedback learning model. And these are the most refined, most polished models that are typically deployed in public sense. This is what your ChatGPT system would look like, or some of the other offerings by the other companies that develop such technologies. And so, as you can see, as you go from the left to the right, there's different types of data sets that are involved. The first step, you have the full internet, which is really a very, very concerning security problem, because we don't have a good handle on what goes on the internet and how reliable the data that is consumed from it is. As you go further to the right, you narrow down the security problem a little bit, but still there is possibility of attackers attacking your data sets in each of these steps in order to influence the behavior of the model. Okay, so then once you have the model, here is an illustration of how the process of adopting a model in the enterprise should look like. The first step is to define the problem you want to tackle with the technology. Then you choose a model. Then you have to adapt and align it to your specific use case, the corporate data that you need to supply there in order to fine-tune it and align it with your needs in the context of the use case that you're working on, and align it with the human feedback from your organization. And finally, you have to integrate it with the infrastructure that's in your environment in order to enable various kinds of automation outcomes. And that's where you essentially optimize and deploy the model for inference. These are the 4 stages, and all of them have to do with introducing yet new different data sets and integrating it in existing infrastructure that opens up opportunities for attackers to influence your model. Okay, so here is, just as an illustration, a high-level architecture of how an LLM system deployed in the enterprise might look like. LLM is not just one component by itself, but it's really made available to the users of the organization through an orchestration library that knows where to direct inputs, whether to the LLM or connect the LLM to external data sources to enable retrieval augmented generation scenarios and access specific corporate documents, databases, or even the World Wide Web in order to respond to specific queries. And of course, there's the integration with external applications in order to enable specific automation scenarios within your enterprise through triggering API calls or email generation or what have you. Or, of course, to offload, in some cases, calculations to modules that are much more capable than the average LLM. It's well known that LLMs cannot handle calculations very reliably, so people typically outsource the calculations to another module and then incorporate them back into the models, into the responses to the user. Okay, so let's go briefly over the different classes of attacks that exist against generative AI system and give you some examples of problems and potential mitigations. Okay, so integrity violations. In here, attacker seeks to interfere with the generative AI systems to force it to misperform against its intended objectives and produce output that aligns with the attacker's objectives. And a typical attack vector here is poisoning attacks. Basically, you change the data that is fed into training the model, and in order to alter its behavior. And it turns out that you don't have to poison a whole lot of it in order to achieve your objectives. A small fraction of a percent is all you need in order to affect its function. And it's also well known that large-scale poisoning is feasible because of the way the internet is structured. As I illustrated in my previous slides, model fine-tuning is also susceptible to poisoning attack. There, we're introducing a bunch of additional data sets, and each one of them can be a target for poisoning. And of course, we all like open models because they very much democratize the access to the technology, but at the same time, they open the door to backdoor poisoning attacks. And here is a reference to a paper which showed what people can do with open source models in order to train them to generate code that is vulnerable from a cybersecurity perspective, vulnerable code, and then camouflage this behavior with layers of safety training, and then be able to trigger the bad behavior upon a specific prompt, a signal from an attacker who will tell the model now turn into a generation of vulnerable code, and then can switch forth and back between generating safe code or strong or robust code and unsafe code or vulnerable code with this signal. And that's pretty concerning if you can think about it. So yes, open models are useful and good, but they come with their own risks. And a different type of attack, not just training time attack, but inference time attack, is through the so-called indirect prompt injection, where your model reaches out to the internet in order to answer specific queries and consumes data from the internet, and that data can be poisoned or adversarially modified in order to produce wrong summaries or generate and propagate disinformation. And there's a reference to a paper that examined that sort of vulnerabilities. Okay, so what can you do to mitigate some of these challenges? Well, security is best addressed comprehensively, including software, data, model supply chains, and network and storage systems. So apply and use provenance and integrity checks on datasets and models. Good techniques from cybersecurity are utilizing cryptographic hashes, even PKI certificates when it is possible. And of course, you should apply data sanitization when every time you consume a data set. Make sure that you have tools that are able to detect and catch adversarially modified data to the extent possible. But at the same time, be aware of the limitations of detecting out of the distribution data. A recent paper in machine learning established that when you have two statistical distributions of data that overlap, you cannot tell the difference. There is no algorithm that can reliably distinguish the two. And that's a result that's been known in physics for quite some time, but now it's extended to machine learning systems. And what it means is that attackers always can have an open door to insert adversarial samples in your data that you will not be able to detect with the data sanitization tools that you have. I'm not saying you should throw away your data sanitization tools. No, you have to use them. Just be aware that they may not give you the full protection that you hope for. Okay, availability breakdown. The idea here is to interfere with the generative AI model to disrupt the ability of other users to process or obtain timely and consistent access to its output or functionality. And one way of doing it is to force the system to perform time-consuming background tasks, heavy calculations or something like this that makes the system unavailable, or to disrupt the output that's produced by the system by inserting or misusing the end of text token so that the model cannot finish the sentence and it generates blank text and therefore makes it unavailable to users. Or you can instruct through indirect prompt injection. An attacker can instruct the model to avoid specific APIs and therefore breaking down those automation scenarios that you instrumented in the first place in your enterprise. All of a sudden, the model will stop issuing emails or something similar to that. Or you can, or attackers may be able to perform indirect prompt injection and instruct the model to replace text with homoglyphs. Instead of using O, they introduce the digit 0. That's what a homoglyph is, and cause a disruption in downstream services that depend on specific correct text. So these are kind of the techniques people can use in order to disrupt the availability to cause an availability breakdown of a generative AI system. What can you do to counter some of these threats, to mitigate these challenges? Well, you have to be able to essentially monitor and be prepared to act when a breach is detected. A good way to go about it is to follow the NIST AI risk management framework to establish a robust governance and structures in the enterprise so that you can inspect the user input, monitor the runtime state of the system, and develop a plan for recovery from a breach. Basically, organizations that are prepared have lower losses when breaches occur than unprepared organizations that are trying to improvise at the time upon a breach. And so be prepared and monitor at all time. Okay. So privacy compromise here, the idea is to gain unauthorized access to restricted or proprietary information that could be model training data, weights, or architecture, or any kind of sensitive information that may be part of the retrieval augmented generation application, and so on. And so during inference time, data extraction, and where the goal is to extract sensitive information leaks, to cause sensitive information leaks, and even to steal some prompts and context stealing, because prompts themselves have become IP subject and have IP protection, and so attackers may be after exfiltrating the prompt so that they could take advantage of it. And of course, through indirect prompt injection, I mentioned this technique many times. You can engage in information gathering, where these attacks against personal assistants that have access to user data or indirect prompting, and then can cause these personal assistants to divulge this data. And unauthorized disclosure is when you have access to specific system where the model is connected to, and you're trying to gain access to sensitive data through calling those APIs or invoking those APIs that the model is connected to in order to exfiltrate the specific data that you are after. So these are just examples. What can you do to mitigate some of that? There are methods that offer a measure of protection, but not full immunity. First, one technique is to train for alignment, and I showed many examples of stages of alignment that you can go through, and these stages can be performed not just once, but sometimes iteratively in order to improve the alignment. Of course, there is no specific guideline for how many times you have to do it in order to become more robust, but that's something that is a subject of research nowadays. Another technique is to be able to monitor and filter out specific prompts and distinguish between user and system prompts, and give higher privilege to system prompts and lesser privilege to user prompts in order to avoid access violations or invoking involuntarily high-value APIs that can exfiltrate data. And of course, there's a number of detection techniques that have been made available recently, and even tools that can detect prompt injections. But again, these are tools that are not fully fully robust. So use them, but be careful to not overly rely on them. And they inspect the user input for malicious attempts and to moderate and jailbreak, firewall the jailbreak behavior, that sort of thing. Okay. So what about the final category of attacks, misuse and abuse violations? Here, the attackers seek to deliberately circumvent the technical restrictions that are imposed by the general device system owner or on its use. And such restrictions are typically designed to prevent the system from producing outputs that could cause harm to others. And so an inference time attack typically based on indirect prompt injection, and these are attempts to for fraud in terms of phishing, masquerading, and deep fakes. We all have heard about these sort of exploits. Malware generation, machine learning models are capable of generating malware to facilitate injection spreading and malware spreading. And of course, manipulation to generate context that can manipulate humans through historical distortion to produce false information, for example, to deny that Einstein won the Nobel Prize, or to steer search results towards specific orientation to cause bias. What can you do to mitigate that? Well, existing methods offer some measure of protection, but again, not full immunity. Major changes in the way the society governs social media are needed to counter these harms effectively, because most of the harms here are not features of the model, but a result of the shortcomings in a way society moderates the discourse on the internet, and therefore information that's generated by these models can be propagated and affect many individuals down the line. What can you do? The specific techniques are reinforcement learning through human feedback. Again, we mentioned it earlier in the slides, and the idea here is to align the model better for the specific use case. Another approach is to filter the retrieved outputs and ensure that a toxic content is detected and eliminated. People are starting to use LLMs as moderators. They are another LLM is monitoring the output from a different LLM, and it tries to detect attacks beyond filtering of just harmful outputs. And of course, interpretability-based approach, where the idea is to go to much more sophisticated statistical methods in order to detect anomaly in the distribution of the information generated by the model in order to detect sophisticated attacks and that sort of thing. So these are the spectrum of techniques that used in this field. Okay, so recently, similar to what I showed you for predictive AI systems, there's been claims about certifiable robustness for LLMs, but these results, even though they appear in the literature, they fly in the face of impossibility results by Gluhoff and others that were published in 2023 that basically say that there is an impossibility of robustness based on these guardrails techniques of ensuring that the system is robust to the extent possible. One way to think of it is through the famous Gödel incompleteness theorem that says that if you have a finite set of rules, think of it as the specific guardrails that are used to control the behavior of the system. If you have a finite set of these rules, there are statements, and if you build a theory based on these rules, there will be statements in your theory that you cannot decide whether they're false or true. And that's what the Gödel theorem says, and you have to sort of come up with yet another set of tools, but then if rules, but if you did that, there'll be another statements that you cannot resolve. So basically, there's an impossibility of having ultimately a robust system by relying on guardrails. And to illustrate this as an example, this is the well-known ASCII art attack that was published in February of this year. So if you ask the model in plain English to give you instructions for how to build a bomb, the model declined and says, no, I cannot give you access. This is a bad question. But if you phrase the same question using ASCII art, as it is illustrated here, how to build a bomb, and instead of writing the word bomb in English, you do some ASCII art composition in order to kind of introduce the same word. And in that case, the model happily gives you the answers that you want. So if you think about it semantically, the difference between the semantic difference between the English phrase how to build a bomb and the ASCII art of how to build a boat is exactly zero. They mean exactly the same thing, but the model acts differently when prompted with the two different prompts. So that's an illustration of how this certifiable robustness idea for LLMs doesn't quite survive here. Okay, so to sum it all up, LLM, friend or foe? Well, it depends on how you flow. With that, let me wrap it up and open up for questions.
Thank you so much, Apostol. And did you generate the limerick, or did you ask an LLM to generate that?
That's a collaboration with an LLM with a Gemini, actually.
Okay. Thank you so much for the presentation. It was very rigorous, and obviously it requires quite a bit of time to digest it. And the technical report, which is on the NIST website, is a great place to start to kind of understand these concepts. And this is an evolving field, and I know we went a little bit over, but I wish we had another hour or so that we could delve into the topics, and we didn't really get a chance to do the Q&A. But I would like to ask one question before we adjourn for the day, if you have a minute. One is, the agentic architectures. Yesterday, I was in an event in Boston, and we were all discussing about agentic architectures. And my graduate thesis, like 20 plus years ago, was on agentic architectures, but we did not have intelligence. We did not have this notion of large language models. It was more trying to figure out how to make different components work to each other in a distributed setting. Now, when it comes down to building architectures, there's a lot of engineering involved, and it's not always going to be the models or the security and the concerns associated with definite specific models. Now, how do you see certifiable robustness kind of play out in the context of agentic architectures, wherein there's a lot of engineering systems involved, distributed systems involved, autonomous systems involved, and decision making is not going to be centralized, and also data access is not going to be centralized. Even to just structure the problem and define the problem, and to even establish basic constructs and formalizing it is going to be a huge challenge. And are we going to just go with heuristics and whatever is possible to test before deploying it, or how do you see the world evolving as we move towards agentic architectures?
That's an excellent question. Thank you, Shrey. I think agentic AI offers an interesting sort of trade-off about security and functionality again. On one hand, when you're talking about agentic AI, you may be able to narrow down the use case for the agent sufficiently enough to have more effective filtering of the admissible inputs that go into the agent in terms of prompts or API calls or whatever. So you have some hope of providing more robust, let's say, filtering of the user input. On the other hand, they are much more actionable and connect to critical systems. So even a small error can cause a much bigger problem than ChatGPT giving you some bad answer here and there, right? So so I think you have a better chance of having more effective filtering and maybe improving the robustness. But on the other hand, you have a much higher risk profile. And so, and on top of that, the underlying technology is still going to be based on the same large language model capabilities of reasoning or limitations of those. And so the same impossibility results that I mentioned in terms of having robust guarantees for security will apply here as well. So you have the same underlying unresolved security problems. You have the capability of narrowing down or filtering better the inputs, but your risk profile on the other end, the actions that result from these inputs is much higher. So you have a really interesting sort of balancing act to play with.
Absolutely. And I know it's a little bit late for you to, Apostle. So I think for the rest of the questions, since you shared your email, you could ask Apostle directly, or if you send us a note, I will send it out to Apostle and see if we could consolidate those answers. And when we share the recording and the slides, we will also put in like the questions and the associated answers there. So just to wrap up today's session, the paper which we discussed predominantly is available on the NIST website. I know Apostle mentioned there's a new version coming out in a little bit, but if you want to download and read through the current version, I would highly recommend it, especially if you're new to the adversarial machine learning realm and want to understand the formal terminologies which are currently in vogue. And since Apostle, Alina, and the whole team has been put on so much time and consolidated all these things, I would say this is a great place to start. The other two announcements I would like to make. Next week's guest lecture will be with two industry professionals, Christoph from TD Bank and Julia Lee, who headed global model risk at State Street Bank. Both of them are in the Boston area. So we would love to kind of, have you guys join to attend this session to understand from a practical perspective how various enterprises are adopting various AI and model risk related aspects. And if you're in the Boston area, on November 7th, there is a whole day workshop hosted by IEEE. It's the Global Tech Forum on AI. And it's primarily going to be a multi-themed session, and there are a lot of interesting speakers. And I'm going to be speaking at the 3 to 5 slot, and I'll be talking about leveraging agentic architectures to continuously upskill and build career resilience in the enterprise. We're building a platform called Q-Skill Bridge, leveraging agentic architectures to enable you to personalize learning, because that's what Quant University does, to take complex topics and break it down into smaller chunks. And we are leveraging artificial intelligence to do it. And I'll describe some of the work we have been doing. So if you're interested, you can join us in Boston on November 7th. We will continue the discussion online. And thank you all for joining in. And Apostle, again, it was a wonderful session. Thank you so much for making time for us and also sharing your immense knowledge and experience. Really appreciate it, and looking forward to joining you all online. And if there are any questions, please reach out to us at info@qsandbox.com. Thanks, everyone, and see you next week. Bye-bye.
Pleasure.